Looks like we are live. Welcome, Dov. Welcome, everyone. Let's see if people are joining. Please put a comment if you're live either in YouTube or LinkedIn. And today for the platform's live stream, we're going to be talking about Karpenter. And we have a special guest today, Dov. Dov, where you're visiting us, and tell us a little bit about yourself.
Hi, Carlos. Yeah, thanks for having me. I'm a solution architect at AWS. I've been working at AWS for over 4 years now, and I specialize in containers. So I talk with many customers about the AWS workload, hear them out, and see if I have suggestions how they can improve. And I speak with many EKS customers across the board.
Yep. I'm also a AWS solutions architect, but today I'm the host of the platforms. So Dov, you'll be our expert today, and welcome Swapnil. Say hi to everyone, and others. Please say hi and tell us where you watching us live. Like we're live. And then if you're on YouTube later watching this, tell us, put in the comments where you're visiting us. And for the audience, you mentioned AWS and EKS. EKS stands for Elastic Kubernetes Service. So it's our managed Kubernetes service in AWS. So that's what you work with on Kubernetes. And for the platform context, a lot of platforms are built for Kubernetes to run compute right on Kubernetes, but also building a platform using Kubernetes API. So today we're going to be talking about a special project called Karpenter, right, Dov?
Yes. So we'll talk about Carpenter and EKS auto scaling in general. And I see many customers that are adopting Carpenter and having great gains in terms of efficiency and cost optimization. And we'll talk about it. Maybe we can start with the slides now.
Yep. Let's go to the slides and talk about
Yeah.
scaling our work. And we're for the context for the audience, we're talking about the in Kubernetes. The audience is familiar with Kubernetes is the worker nodes, the servers, right, where kubelet runs. And in this context, is we'll be talking about the cloud, where it's more elastic to bring in worker nodes and get them in and out. Versus if you are on premise, either you have a room full of servers and you cannot fit more, right? So it's not easy to move servers around. So this is for the cloud. Yep.
Exactly. So if we're talking about platform engineering, we're enabling the developers to become self-service and deploy the applications to the production environment self-service. An environment like that must be dynamic. It can't be static because if you have a static amount of instances, the developers can't be self-service. They need to check with the infrastructure team before they deploy something. An autoscaler like Karpenter allows the workload to be dynamic. The number of instances can go up and down according to the dynamic usage. And autoscaling is one way that Karpenter enables to reduce costs and increase efficiency. But there are other ways to reduce cost. One way is to use reserved instances or saving plans. These are methods that you need to commit to a certain amount of instances for a year or 3 years, and then you get a discount. But if we're talking about dynamic workloads, we don't want to always commit to a certain amount of instances. So let's look at other ways to save, to reduce EKS costs. The other ways to use, one of the ways to use Graviton instances. Graviton instances are ARM-based instances, which were designed by AWS, but are based on the standard ARM instances. And they have a higher cost efficiency than the parallel Intel instances. So that can, in certain cases, reduce costs.
Yeah, and it's been lately. It's been a movement to for the container community to compile their applications, right? Build their Docker containers and containers with ARM64 and AMD64. ARM64, you can build an image, right? A container image that is multi-architecture. That's usually kind of like the best practice. And this episode is talking about best practice. So one best practice that we can start with is like build your containers for ARM64. If you don't want AMD64, but maybe you are in transitioning, right, from on-premise to on the cloud, or like the application runs in different environments. So if you build a multi-architecture, then ARM64 will run out of the box. The same image can be used in AMD64, but ARM64 cost effective, right? It can give you more value, and it performs more, and it's usually less. The cost is less.
Yeah, and Carpenter makes it easy to work with ARM instances and also with Graviton instances and also with a mixed workload. You can have, if you have Intel-based instances and you want to have like a mixed workload of Intel and Graviton instances, Carpenter makes it easy. Another thing that Carpenter helps with is using spot instances. Now, spot instances are a spare capacity that AWS has, and because it's a spare capacity that currently no one is using, AWS gives it at a significant discount. These discounts can be from 60 to above 80% discount on the price of the instance. These are higher discounts than the discounts for the saving plans of those instances that I talked about before. There's only one catch about spot instances. Because there are spare instances that AWS gives them at a discounted price, AWS reserves the right to interrupt them. That means that in any given moment, you might get an interruption, and that means that the instance, there'll be a 2-minute notification before the interruption, and after 2 minutes, the instance will be terminated. So AWS can give you this instance in a very high discount, but it can also take it away. Because of this interruption thing, maybe 2 years ago, 3 years, customers would think about Spot as something that you can, it's nice for testing, okay? If you, in testing environment, it's okay. Worst case instance will be interrupted. You can run the tests again, no big deal. But customers wouldn't think about running them in production. A trend we're seeing in the recent years is that customers more and more use Spot in production. So we see some large customers using almost 100% of their instances in Spot in their highly available mission-critical production workloads. How is that possible? That's possible with the help of Karpenter, which is very smart about handling Spot instances, giving you instances with high capacity. That means there's a low chance that they'll be interrupted. And if they are interrupted, Karpenter can quickly, in that 2-minute notification period, replace a Spot instance with a different instance. So you always have your capacity of instances for your workloads.
Yep. So as a best practice, use easy to spot, lowest the cost, and also make your containers, right, that can handle the signal of like being in Kubernetes to handle the shutdown signal, right, that kubelet will send to your containers, so you can handle the load, and also architect your applications to take advantage of that, of like having horizontally applications that at any time they can like get shut down, but there's other applications handling the traffic and also handling like even batch. I've seen batch jobs taking advantage of Spot where like they have like that 2-minute signal, right, that they can do a checkpoint to some state, and then when it comes back in another server, it will pick up where it left, and things using things like SQS. So yeah, these are kind of like the primary use cases. What would you use Karpenter? And I think we're going to talk a little bit more of like picking up like the strategy that Karpenter brings of like try to get a spot, but in the case that you cannot find a spot, right, within requirements, then use on demand. And we'll talk a little bit more about that moving forward.
We'll talk about that, yeah. We'll talk about that, but yeah, the main point is Karpenter allows you to work with spot instances in production, as long as Carlos said, you architect your application in a way that is can handle that. So before we talk about Karpenter, let's talk about take a step back and talk about how auto-scaling in general works in Kubernetes environment. This is in any Kubernetes environment, not just in EKS. So scaling in Kubernetes is composed of two different mechanisms. One mechanism is pod scaling. Pod scaling, and the default example is the HPA, or the horizontal pod autoscaler. Pod scaling adds more pods to your cluster. So let's say your pods are running and you get more and more traffic, and the CPU goes up in the pods. And eventually, when the CPU crosses a certain threshold, like 70% or 60% CPU, the HPA will add more pods, and then the load from the load balancer will distribute between more pods, and each pod will have less CPU, so it will add more pods to handle the traffic. Okay, and there is a modern open source alternative to HPA. HPA is also open source, but there's a newer alternative called KEDA. I'll talk about KEDA in a minute. But if you have a static amount of instances and the HPA adds more pods, eventually there'll be no more room in the cluster. If you have 10 nodes, eventually if you add more and more pods, there won't be room for the pods in this cluster because it has a static amount of instances. So the other part of autoscaling is node scaling, which adds more nodes or more instances. And what is the trigger for node scaling? If the trigger for pod scaling is CPU, the trigger for node scaling is pending pods. So when we reached the scenario that I described, where the HPA added more pods, but the pods don't have anywhere to be, the pods will be in pending state. When the pods are in pending state, the node scaler will pop in and add more instances. Now, also here we have the classic Kubernetes cluster autoscaler, and then there's a more modern alternative called Karpenter, which we'll elaborate on today. So let's talk about HPA and cluster autoscaler, and then we'll go to Karpenter. Okay, so the HPA scales by CPU, but some customers want CPU is not enough. They want to scale by other metrics. For example, for batch workloads, as Carlos mentioned, some customers want to scale by the queue length, or some customers want to scale by other Prometheus metric, I don't know, number of requests or whatever. KEDA has many integrations to cloud providers and different tools, and KEDA can allow the pod scaling to happen according to any metric like SQS, queue length, etc. Okay, so if you just use CPU, HPA is okay. If you want to scale by other metrics, KEDA is a great open source tool. Now, let's talk about the classic cluster autoscaler and what are its limitations. Why is Karpenter needed at all? So the cluster autoscaler, when there are pending pods, the cluster autoscaler kicks in.
And before that, like to clarify for the audience, when you say scheduler and HPA, in Kubernetes, right? You can create pods and start creating pods, and the kube scheduler in Kubernetes will schedule those pods. Schedule meaning like placement, right? We'll place this pod on the different nodes until they fill up of like the requesting of CPUs that they are requesting, or memory, right? How much capacity, spare capacity the nodes have, and to a point that pods will go into, you do kubectl get pods, right? They will see the status instead of running that people see, they will see pending. And at that point, Kubernetes, the kube scheduler will raise their hands like, I don't know how to get more nodes into this cluster, right? There needs to be an external entity or something else than the Kubernetes core from the upstream to get more nodes into the cluster so that it can schedule it to it. So that's where like the pending pods is the trigger, like you mentioned. On like you have pending pods, then that would trigger a controller. And for the most time, people have been using the CA, cluster autoscaler. This is from upstream Kubernetes, and it supported multiple cloud providers. In this case, also in AWS. And it will see that there's a pod pending. But talk a little bit more about cluster autoscaler and manage node group, like the number of instance or the type of instances, right, to configure that, and the time that it takes for the cluster autoscaler to get me a new node to place the pod.
Sure. So cluster autoscaler works with an abstraction called managed node groups. You need to specify a managed node group, and a managed node group is a group of instances that can scale up and down, like it has an autoscaling group behind the scenes, and it's composed of instances of a certain type. You can't mix different instances from different sizes and same type. You should, the best practice is to use instances of same type in a managed node group. And also, a managed node group can be either on demand or spot. You can't tell it, okay, give me spot, but if there's no spot, I want the same managed node group to give me an on-demand instance instead. It's one type per managed node group. You can have multiple managed node groups in your cluster, but that can complicate the setup. So
that's the complication I was talking about. A lot of people that we see using cluster autoscaler, you see in the picture here, we should have put like more boxes for the managed node group, right? They will create a managed node group for servers that have like 2 CPUs and 4 gigs of memory, and then another spot, and then another node group on demand, another group for worker nodes that maybe has 4 CPUs and 8 gig of memory, and then the next managed node group is the GPUs. So cluster autoscaler will have like different groups because have to be the same type, and that, like you said, it complicates things. You end up with a lot of like ASGs or managed node groups, and then cluster autoscaler will need to go to, is this spot fits here or fits here or fits here, and try to figure out like from the given managed node groups. And in cloud providers like AWS and others, right, the amount of mix of different types of servers, right, it's in the hundreds of the things that you can get multiplied by 2, right? Spare capacity versus not spare capacity.
Exactly, and another point is if you're using spot instances, you want to have the what we call diversification. You want to allow many different types of instances because, as I said before, if there's no capacity for one type of spot instances, you want other instances to be available. You don't want to be tied up to a specific instance type like managed node group makes you. So here comes Karpenter. Karpenter is a project that was created by AWS as a modern alternative to the cluster autoscaler, and it was actually recently donated to the 2 announcements. One, a while ago, it was donated to the open source community, to the CNCF. And there's already, for example, Karpenter for Azure. So it's not only an AWS proprietary thing, it's an open source product that can work on multiple cloud providers. And the other announcement is Karpenter, just last week was announced V1. Now, Karpenter has been GA, generally available GA for a while now, but now it's also officially V1. So it's a good time to look into Karpenter. So Karpenter does a few things. One of them, it does cost optimization.
And I posted a link there for Karpenter V1.0, and it's for Karpenter, right? Karpenter, the open source project, which works in multiple cloud providers.
Yeah.
So the API now is stable, right?
Yeah. So Karpenter does cost optimization by various ways. One of them is how it handles spot instances, and we'll talk about them later on. And another interesting thing that is relevant not only to spot, even if you're using on-demand instances, Karpenter will do what's called consolidation. I'll show how it works, but basically it doesn't only do the scale up and scale down. Also, in the down periods, it will always look how it can optimize your cluster as it goes and bin pack your cluster in a more efficient way to reduce your number of instances and reduce your cost. It's all the time looking for ways to optimize your cluster actively. It also supports multiple workloads like machine learning workloads, Graviton workloads, etc. And it helps with the general maintenance of your cluster by automating the upgrade and patching of instances. So that's another benefit, not only scaling, but also the general maintenance of your cluster is easier with Karpenter.
Yeah,
As we
upgrades is
said,
one of the
Karpenter,
best features when I talk to end users, and they ask me before Karpenter, right, existed, right? They're asking me like, how do I handle upgrades of the data plane of these worker nodes? So it was typically like you have to create the ASG, a new AMI, and manage like all instances have to go at the same time. In this case, Karpenter is monitoring, and you can like configure like how long do you want to have a node being alive before you destroy it, right? And then it will map to the version, so you don't have to like calculate the version of Kubernetes. It will follow the control plane by default, but at the same time you can leave it behind and follow the best practice of like, not best practice, but a lot of people want to not disturb the data plane that much to when you every time you upgrade the control plane, right? So you can upgrade the control plane, leave the data nodes n-1 version of Kubernetes, upgrade the control plane again, and then this is n-2, and then upgrade the data plane. So you have a different life cycle for both.
Yeah. The upgrade is can be a heavy maintenance task, and any help with the upgrade process by Karpenter can make cluster administration easier. So the way Karpenter works, it's not confined to it doesn't use auto-scaling groups or managed node groups. It listens to pending pods, just like the cluster autoscaler. When there are pending pods, it calculates how much CPU and memory let's say now it sees 8 pending pods, and these pending pods total to a certain amount of CPUs and memory that they need. Karpenter calculates what is the total amount of CPU and memory all the pending pods need, and it calls directly the EC2 Fleet API. So there's not this intermediary of managed node group, auto-scaling groups, and it just spins up the instances that fit the size of the pending pods. So it spins up the number of instances. Maybe it will spin up one large one and another small one, and to fit exactly the pending pods that need to be running.
Yeah, one more difference on that is the Karpenter is faster, right? People have said that when they want to scale fast, that they have a burst of that they want to get more nodes. Cluster autoscaler will tell the ASG. The ASG eventually will bring the number of nodes, right? It takes longer for that. Karpenter like cuts into the middle, right? It goes from pending pod directly to the API that gets you the specific node type. So it's faster to get a node up and ready and the pod to be ready, right? It's faster to get it a pod up and running and when you're scaling out.
Yeah, I see a question in the chat. Is Karpenter available for, so it's Karpenter with a K, not with a C, like Kubernetes. And they ask, is Karpenter available for VMware on-prem? I'm not aware. I know Karpenter is available for Azure. I'm not aware if I don't think it's available for VMware, but since it's open source, there's no problem for the community to create it for any other tool and also on premise. But currently, I'm not aware that it's available. So I want to deep dive into a little bit about how the configuration looks. And this is a basic component of Karpenter, the node pool. And here we can see that we can define on the top the instance family I want to use. So I want to use C6, M6, and R6. I would advise to use as much instance families as possible. And then I can exclude. I don't want instances that are nano, micro, or small. I work in these two availability zones. I allow AMD, which are Intel and AMD instances, and ARM, which is Graviton instances, so it's a mixed workload. And the last configuration says that the capacity type can be spot or on demand. So what that means, Karpenter will prioritize spot because spot is cheaper. But if there's no spot available and it checked all the families, C6, M6, R6, it will do what we call fallback to on-demand. So you'll get an on-demand instance which is more expensive, but you will get this high availability that you expect, and you won't be stuck without instances. Now let's look a little bit about on consolidation, which is a very interesting feature that Karpenter does. Yeah.
One point is if you go back to the slide, is the ability to specify multiple instances, right? And also like you see the AMD and AMD 64. So and the fact that this is YAML, right? This is Kubernetes resources. So you're actually using Kubernetes to define now your cloud infrastructure. So this is a way of like using Kubernetes APIs to manage the hardware that you get, the infrastructure that you have, that you can like deploy these things with like things like GitOps, for example, right? And then you have your infrastructure in the declarative manner using Kubernetes APIs, where because for autoscaler, you have to do different type of tools, right? Like Terraform and things like that to define the instance types and the requirements. So this brings you more native into Kubernetes tooling.
Yeah, and it also makes it, because it's declarative, it makes it easy to change. You can now you don't want to use R6 anymore. You want to use R7. You can change the configuration to R7, and from now on, Karpenter will have R7 in its pool of options and not R6. So let's talk about consolidation, and let's look at this cluster of 4 instances. Let's assume each instance has 4 CPU. Each pod takes 1 CPU, just for the example. And we see we have one instance that is full. It's fully utilized, but there are other 3 instances that are underutilized. Okay, we're paying for the whole instance, but just one pod is running on the 2 left instances. If we define the consolidation feature, when empty or underutilized, consolidate, Karpenter will detect this underutilized instances. It will see, hey, I can move the 2 pods on the right to the second instance because it also has free room. It will move the pods to the second instance until it's full, and then it will terminate the 2 instances that remained empty. And by that, it will reduce the size of the cluster and save you costs without you having to touch anything. It will also,
so just with that little animation, right? You went from paying 100% to half the price, right? All these worker nodes, and a Karpenter did that automatically by detecting how can I fit. So this is the first level. Like this is like people get excited about this, but it gets more interesting, right? For the next use case. But at least in this case, half of the cost went away, right?
Yep, half of the cost just automatically. And we see, I see customers in production adopting Karpenter, and they can see the cost reduction in the workloads happening all by its own. Let's look about another use case. Okay, the next use case is we have on the left instance that is fully utilized. On the right, we have instance that is underutilized, but there's no room to move that single pod on the right to another existing instance. There's no available room. In that case, Karpenter can spin up a small instance, maybe an instance with 2 CPU, move the pod to the smaller instance, and delete the large instance. So you're not stuck with a large instance, because after your clusters scaled up and then scaled down, you might get situations where you have large instances with 1 or 2 pods. So Karpenter will try to consolidate them, and it can also reduce the size of the instance. Karpenter will also respect pod disruption budgets, so which are a feature of Kubernetes that will make sure that you have a number of pods always available, a minimum number of pods in the deployment always available.
Yeah, one interesting thing, if you are interested to looking into the code, this code is open source, is in GitHub, and is now upstairs in CNCF. There's a concept of simulation. So Carpenter is very smart that is doing simulations behind the scenes. So it's just taking like what it is and then tries to do the code. Is like doing simulations to see what is the best use case for the end result. If I move this spot here, if I move that node here, if I get a different size, if I get a bigger size, how do I do the beam packing, right? So he's doing simulations behind the scenes. Very interesting. If you like to learn more about it, the code is available in GitHub to understand more about that. But that's kind of like the core of Carpenter behind the scenes that is doing simulations, multiple simulations to get what is the end result that it will meet all the requirements, like pod disruption budgets, anti-affinity, topology spread, constraints, to follow the requirements to see that's the end result meets the requirement that is configured by the administrator.
Yeah, I heard behind the scenes that it's interesting computer science problem because bin packing like this, it's an NP complete program and problem. And so there's various heuristics to do this simulation and give you the optimized end result.
I think there's a question on asking for tutorials or Carpenter.
Okay, so in the end of this talk, we'll have a slide with different tutorials and workshops and follow-ups. We'll share everything. Okay, so I just want to say that some customers say, okay, I want to use Carpenter to scale up and down, but I don't want the consolidation because I don't want Carpenter to move my pods from place to place, even if it will reduce my cost. I don't. So you can disable consolidation and have Karpenter work only in scaling events. Okay, the last example I think is let's say we have spot instances, and we mentioned this example before, and there's no capacity. We got an interruption. Karpenter will check if there's other types of instances that have capacity. It will spin the other type of instances instead. But if there's no spot capacity at all, it will spin up on-demand instances. So we will have instances available, and we won't be left without instances. Now, now, what happens if the spot, we had an interruption, and now there's many different kinds of spot instances that Karpenter can spin up for us. Karpenter has a strategy called price capacity optimized. It will choose which new spot instance will choose to replace our current instance. It will choose the instance types that has a combination of lowest price and they have a high capacity. So that means that they have a low chance of being interrupted in the short term. So it knows to choose the best instances that have a high capacity and low cost. Okay.
That's a question.
Yeah, I think
go back to that scenario. So this is to avoid, like, if you have pending pods, right, and you're in the node pool, you put your requirements. So like the requirements are like strict. Like I only allow these instance types or in this region. It could be that our availability zone. It could be that in certain availability, if you make it as a best practice, if you make it very constrained of the, you don't diversify, right? You say like, I only want M machines, right? Or compute optimized, and only this size, and only this availability zone, right? Karpenter will say like, I cannot find a spot at this time in this constraint, right? So as a best practice, you want to make it like all possible instances types, right? More diversified, make the images, the instances even bigger, because it will do the bin packing, right? It would accommodate them inside of it. And then, but the key is like, in the past, when cluster autoscaler maybe manage node groups, people will configure only spot and not have on demand. And then if there were at certain points there was a pod pending and didn't find with that constraint, that specific instance, it will like the pod will stay pending forever, and maybe you have downtime, maybe you cannot sustain the workload, right? So in this case, Karpenter is one of the solutions that came to solve that issue of like, if I cannot, I will try to do spot, but if I cannot find it, then I would use an on demand, and on demand is always available, probably available in that specific constraint.
Yeah. So two more questions. Does GCP use Karpenter? Currently, as far as I know, not. And will Karpenter respect taints and affinities and anti-affinities? Yes, Karpenter will respect the Kubernetes constants like taints, affinities, and anti-affinities. So the last part, we want to share some links that will help you deep dive into Karpenter and learn about the best practices. The first link is AWS EKS best practices. We have a guide on general EKS best practices. I recommend this guide, and it has a chapter on Karpenter best practices. The second link is called Karpenter Blueprints. It has a set of examples of how to set up the node pool YAML that I showed before for different scenarios. Let's say you want to use a GPU, so how to use it with GPU. Different scenarios are presented with the YAML examples in the blueprints. The third link is a containers roadmap. We have open source, publicly available roadmap for everything related to EKS and Karpenter also, so you can see what we're working on, suggest your own features in the container roadmap. And lastly, we have the Karpenter workshop. We have a EKS workshop, and it has a Karpenter chapter where you can try it out yourself and follow tutorials to set up Karpenter.
Yeah, and then also if you are in the CNCF community and use the CNCF Slack or Kubernetes Slack, it's the Kubernetes Slack, the Kubernetes channel. In the Kubernetes Slack workspace, there's a channel called Karpenter, and then you can interact with the community there. Also, if you want to contribute, right? Anyone can contribute to open source. If you're interested about like contributing to open source, either with docs or code or community work, there's a Karpenter-dev that you can talk to the maintainers there. Do we have a question? See a question about 4 replicas for high availability, and I don't know if we can show that. It says I have a deployment of 4 replicas for high availability, and I want to keep 4 replicas in different nodes. Do we have any methods to honor this in Karpenter, because I can manage this with taint and affinities? So yeah, Dov, you want to take that one, or I can take it?
Yes. So you can create. So the question is, they want to have they have a deployment of 4 pods, and they want each pod to be on a different instance. They don't want pods from the same deployment to be on the same instance for high availability reasons. If the instance goes down, only one pod will go down. The answer is yes. You can define node anti-affinity on this deployment that will make each pod be on a different instance, and Karpenter will completely respect this anti-affinity.
Yeah, it's more concern of a kube scheduler, right? So the kube scheduler, if it would deploy the 4 pods, and let's say that it's handling the 4th one, and the 4th one, it fits into one of the other 3 that there's already a pod, the scheduler will say, I cannot put it in there, right? So Karpenter will see that it's pending. It will see that the reason that it's pending is because it doesn't fit there, and that's where you get the new node, and then the pod goes there. So that's why it needs to work both aspects of it, and it's not as simple as like writing a single program, right? Instruction set. Kubernetes is very powerful in terms of like workloads and placements, and then Karpenter comes in respecting that, like Dov says, respecting those constraints or requirements to get you a new node, right? When is the time to get you a new node, and then what size of that node, if it's spot or on demand. So that's the concerns of Karpenter, getting you a new node provision very quickly, because it talks to the Fleet API. And so I'm talking about best practices, right? We suggest to you to use the cloud provider AMI image, the operating system image, to keep the boot up time of that server fast, and not put a lot of things in that server, or like a boot time to put things. Also, Carpenter will handle the provisioning will be the same as managed node group. The aspect of like there's certain agents that need to come first, right? The VPC CNI and other agents from a third party provider, and then your workload will come in. So that ordering is handled. But as a best practice, right? Do all the things that you can to make, if you have a requirement to have that pod up and ready as fast as possible, then you have to take care of the node, right? And the operating system of that server booting up. You have more questions? Yeah, I think that's it. We were able to cover a few questions. A lot of people joined. This will be recorded, so reach out, and LinkedIn, both for me, Dov and Carlos. I mean, myself, you can find me in LinkedIn, also Twitter, and follow the platformers community in LinkedIn. We'll be doing more episodes. And in terms of Carpenter, there's a lot of resources out there if you want to learn, like Dov shared, or you want to interact with the open source community. So with that, I would say, Dov, thank you so much for giving us your time. I know it's late where you're located, but thank you so much for joining us today and handling the questions and giving us an overview and best practices on Carpenter for Kubernetes.
Thanks for having me. I enjoyed it.
Yep. Thank you so much. See you folks. On to the next one.
See you.
Okay.
Bye-bye.